for today, and our lesson today is going to be graphing a quadratic function. So our objective today is to graph a quadratic function from vertex form. And I really should modify this because we're not going to actually graph, we're going to more sketch. So we're going to sketch a quadratic function from vertex form. All right, so let's talk about what is the parent function. So as always, the parent function for a quadratic is y equals x squared. Not always, but it is. That's the parent function, y equals x squared. The domain, so we have a graph of a y equals x squared, and the domain, we can see the domain for a quadratic will always be negative infinity to infinity, just like an absolute value function. The range will change depending upon where the vertex is, just like an absolute value function. So in this particular case, the parent function has a range. We see that it starts at 0 and then it goes towards infinity, and 0 is included. Where is it increasing? So it's going to be very similar to the absolute value. It's increasing on the second part of the graph. It increases here. So it's increasing from 0 to infinity. It's decreasing from negative infinity to 0. Again, I like to say 0 is neither increasing or decreasing, and there's some debate about that in the math community, but I'm the one grading your test. So we're going to say that it is neither increasing or decreasing at 0. Our vertex is 0, 0. Again, vertex is that max or min point, so that's our vertex. The axis of symmetry is still the imaginary line that cuts it in half, so our axis of symmetry is x equals 0. And all quadratics are continuous functions, just like absolute value. They're all continuous function. Its end behavior is similar again to absolute value. As x approaches positive infinity, so as x goes to positive infinity, the function goes towards infinity. As x goes towards negative infinity, the function goes towards positive infinity. The solution, just like on an absolute value, the solution is where it crosses the x-axis. Crosses or intersects the x-axis. So in this case, our solution is 0. Is x equals 0. The vertex form is going to once again be very similar to what we saw with the absolute value. It's going to be y equals x minus h squared plus k. And there's an a in front as well. So the a indicates how fast the graph rises. So just like an absolute value, if a is greater than 1, the absolute value of a is greater than 1, then your graph is going to be skinnier or more narrow. The absolute value of a is less than 1, your graph is going to be more wider. If the absolute value of a is equal to 1, it's going to be the same. It's going to be the same as what you see in the graph. Okay? H, again, will represent the x-coordinate of vertex. And if we have minus a, then it's a move right. Plus a is a move left. So the H indicates our horizontal shift. K indicates the y-coordinate of the vertex. So it's just like absolute value. If we have plus K, it moves the graph up. I said A's here. This should have been plus H. Sorry. And I don't want to go back and do this again. But I'm just going to say that this is going to be minus H and plus H there. Sorry about that. All right, so plus K moves the graph up, and minus K will move it down. Okay, so it's just like the vertex form of absolute value. So we're going to just kind of graph a couple of these. So if we have y equals x squared minus 3, the transformation, because this can also be written as x minus 0 squared minus 3, our transformation is 0 units to the left or to the right and 3 units down. It's about the same, it's the same width. So we're going to start at negative 3. Like that, something like that, and then we graph. It's symmetrical about that x-axis, about the y-axis, sorry. So the slope, there is no slope. I don't know why I have that there. Oh, because I copied and pasted, so you can just ignore that. The domain for all these will be negative infinity to infinity. The range will go from negative 3 included to infinity. Remember that negative 3 comes from that horizontal, vertical shift. The axis of symmetry is x equals 0. Our vertex is 0, negative 3. And we can see that this is a minimum value because it goes down to a minimum and then it goes back up. It's continuous. And as x goes towards infinity, our graph goes towards infinity. As x goes towards negative infinity, our graph goes towards negative infinity. It is increasing from 0 to infinity and decreasing from negative infinity to 0. The solutions are hard to tell when we are graphing it this way, but from experience, I know that my solutions are going to be radical 3 and negative radical 3. How do I know that? Just take my word on it. What I can do is if I do x squared minus 3 is equal to 0, I add 3 to both sides, and I get x squared is equal to 3. And then to find the value of that, I have to take the square root of both sides. So that's how I found that. I'm not really asking you to do that in this unit. That's more of a next unit thing. Okay? So our transformation, if we look at the second one, our transformation, y equals 2x squared plus 2. So we know that we can write this as 2x minus 0 squared plus 2. So I am moving this up 2 units. And because A is 2, it's going to be a little more narrow. So we call that a vertical stretch. Because I'm going to make the graph just a little bit more narrow, and this is stretching the y value of that. Our domain is the same. Oh, let's graph it and see what our range is. So we're going to start at 2. Now again, I'm just sketching this, so I don't know exactly what it looks like, but I know it's going to be skinnier than the one I did before. So I'm going to say it's going to look something like that. It's just a sketch. Our axis of symmetry will be x equals 0 again. Our vertex is 0, 2, and it's still a minimum because it goes down and comes back up. It's continuous, yes, because they're all continuous, and infinity, infinity. It's increasing, so this is increasing, this is decreasing, so it's increasing from 0 to infinity, It's decreasing from negative infinity to 0.